All right, so this is a basic overview of atoms and the element squares that are on the periodic table. A nice, big, broad overview of kind of everything we did in that PhET simulation. I know some of you like to take notes and have things in your notebooks, so this may be just a nice organized way to get things together. Let's start out real broad by going ahead and defining the term matter, which is just anything that has mass and takes up space. The word matter is actually found in the definition of chemistry. The definition of chemistry is the study of matter and the changes that it undergoes. So obviously chemistry is centered around matter itself. So fundamentally it's just really everything we can touch, see, taste, and feel. We call everything in that category matter. And even the tiny little things that make up what we touch, see, taste, and feel, we call that matter as well. So atoms in particular are the things that make up matter, so we really discuss those quite a bit. So atoms are just simply defined as the building blocks of matter. And most matter is a collection of atoms in a specific arrangement that allows them to have distinct properties that we can then analyze, test, and change and utilize to our benefit. So taking a look at the periodic table here on the bottom of the page, we have a bunch of different elements, and each one of those elements is made up of a different type or specific creation of an atom. We always say in chemistry that not all atoms are created equal, that a collection of nearly identical atoms, so atoms that almost look 100% alike, we call these things elements. And they're organized on the periodic table. As long as two atoms have the same number of protons, then those two atoms will be of the same element. So for instance, if we have an atom that has, let's see, 2 protons, then without a doubt, unequivocally, that particular atom will be a helium atom. If we go ahead and change the number of protons to, let's say, 6 protons, then the actual identity of the element will change and it'll be unequivocally a carbon atom. Now, within those atoms, there are some changes that can take place, like exactly how many neutrons there are. Some carbon atoms will have 6 neutrons. On the other hand, some carbon atoms will actually have 7 neutrons. And a very, very small amount of carbon atoms will actually have 8 neutrons. But in each one of those cases, the element itself is still carbon. Why? Because the protons didn't change. Just like neutrons changing and elements staying the same, we can also change electrons. So most neutral, or all neutral carbon atoms have 6 electrons. But sometimes we can either steal electrons or donate electrons to carbon, and in that case that changes this total amount of electrons. Again, at the end of the day, we still have a carbon atom because the protons have stayed the same. So backing up here, these collections of atoms, also known as elements, are then organized on the periodic table, and we'll talk a lot more about periodic table organization later on down the road. But the light stuff is up here at the top of the table. The heavy stuff is down there at the bottom of the table. And you kind of read the periodic table like you would read a book, left to right, up and down. So left to right, and then up and down. So hydrogen's number 1, and helium's number 2, and lithium's number 3, beryllium is 4, 5, 6, 7, so on and so forth. So it's really kind of an ingenious organization of all the elements known in the universe. So let's take a look at an elemental symbol. Now you're working with these in your PhET simulation, so this should kind of be a review. Just to define the atomic number, it's the number of protons in a particular element, and the atomic number again doesn't change for that element. So it's right there for oxygen, it's 8. So those two are synonymous with each other. You hear oxygen, right away you should think 8 protons. Now the atomic mass is the other key number in an elemental symbol or an elemental square. And in this particular elemental square, it's shown here on the bottom. It's actually not a whole number, it's 15.999. And that's due to the fact that the amount of neutrons that an oxygen atom has can actually be altered, can change. And when those neutrons change, we have something called an isotope. So the atomic mass is specifically defined as the average mass of isotopes of an element. And we're actually going to do a lab, and we'll find the average mass of a fictitious element, and you'll see that that average mass will not come out to be a whole number. It'll be a decimal number. We'll also use the example of calculating your grade in this class that doesn't come out to be a whole number either. Isotopes, to get a crude definition, just same number of protons but a different number of neutrons. That's how we go ahead and define isotopes. So you can have a carbon atom, and it's got 6 neutrons or 7 neutrons or 8 neutrons. All of those carbon atoms are still carbon, but they're different isotopes of each other. Some people ask, okay, so this is the atomic mass, right? The atomic mass. So that must be, well, what's in an atom? Protons and neutrons and electrons. So that must be the mass of all 3 of those things right there. Not necessarily. It kind of is, but for our purposes, the only 2 subatomic particles that give this mass right there are actually just the protons plus the neutrons. The electrons are so incredibly small that they don't lend any mass to the overall size of the atom as far as we're concerned. Now, if you're really getting particular, yes, they do lend a little bit of mass. But for our purposes, we only think of the neutrons and the protons lending to the atomic mass. All right, that's 2.1.